Hi, I'm Ryan Nickel, CTO at DSA Ocean, and today we're going to talk about ship motion analysis and more specifically ship design and hydrodynamics preprocessing with ShipMo 3D. Here's an agenda. We're going to go over a review of ship motion and the ship motion analysis process, and we're going to talk a little bit about the ShipMo 3D structure, and then go through the steps of ship design and hydrodynamics preprocessing. So what does the ship motion analysis process look like? We use this as a roadmap, this little flow chart, to give an idea of where we are in the process that's involved. Today we're going to focus on ship design and hydrodynamics pre-processing together. The reason for that is that they're fairly well integrated with each other as you go through ShipMo 3D. So you do a little bit of ship design, you do a little bit of hydrodynamics pre-processing, you go over to ship design again and assemble the full ship model. And this is ahead of doing the seakeeping and maneuvering analysis, which we'll cover in another presentation. So the workflow process, very generally, just as a reminder, you go through the process creating the hull mesh, which you might do through offsets from a lines plan as a input file, or you may have created your specific hull mesh with another tool like Rhino 3D. Has to be in an OBJ file format, which is an open file format. The next step was then computing the wave radiation diffraction. Wave radiation behind the scenes is calculated in a calm sea and moving the ship in unit directions to evaluate the effects and wave forces that are radiated away from the hull in different degrees of freedom. And then the diffraction calculation, which is where the ship is still and incident ocean waves are generated, and the interaction effects with the hull from a wide range of frequencies and forward speeds are resolved. So the diffraction is like what happens to the wave as it deflects around the hull and the force that it creates. Finally, there's an assembly of the ship model. This is the appendages like bilge keels, skags, rudders, and things like that, as well as propeller models are all assembled. These represent viscous models and effects that are added and then superimposed on the entire ship model and used in resolving the total motion of the ship, in addition to the wave radiation and diffraction forces. So let's talk quickly about the structure of ShipMo 3D as a program. So ShipMo 3D consists of several application programs, and each application is used to configure information and compute data used elsewhere. Typically, we go through a very similar process in working with these applications one after the other. And I'm going to show a few of them in order of typical use. So there's a lot to go through. When you start off with project settings, panel hull, panel lid, rad diff, and so on, we're going to focus on these ones in the ship design and hydrodynamics pre-processing stage. And we'll go through them, the important ones, shortly. These other ones are important when we get into the actual specific sea keeping and maneuvering analysis. So let's get into the specifics with ship design. So when you first open up ShipMo 3D, you're faced with setting fundamentals of the ship in your project settings, like what's the length between perpendiculars, station of the aft perpendicular, and draft at midships, center of gravity, and trim, and so on. This is a little graphic to kind of give an idea of what those parameters look like on a typical monohull vessel. Then you get into the first application, panel hull, and this is all about generating the hydrodynamic mesh that's required for calculating wave excitation forces, those incident loads, diffraction loads, and wave radiation loads. So you generate these hull lines with information that you have on the vessel through a lines plan. This is the Esso Osaka hull lines. There's a sample project that you can look at in detail. There's a lot of information here. The one way to generate these files is through a patch file, and you describe patches of the hull surface in groups. So this blue region with many hull lines defined at different stations is one patch, and then you've got others for the details of the bow as well as the transom. it does take a bit of work to go through this process, but it's really nice because you can immediately adjust the meshing parameters once the hull lines are all set up in the hull lines file. There is a panel limit on the number of panels you can use. That's kind of necessary because of memory limitations that many computers have. The diffraction and radiation calculations can use a lot of, yeah, there's processing power, but memory as well. So another way that you can provide input is through an OBJ mesh file where you've just produced the mesh directly, and oftentimes people use Rhino 3D for this, but there's many other programs that will allow you to easily create a mesh directly. One disadvantage is that that's the mesh you have to work with. If you want to make any changes, you have to go back to the tool used and refine the mesh accordingly as needed. Note that Shipmo 3D will automatically refine the mesh at the water line of the vessel. That's really crucial for improving numerical accuracy and reducing noise in the calculations. And you can see an example of a sample project with the KCS, that's the Creso container ship vessel, where an OBJ mesh file has been generated for you, and you can see how it works with that. This was generated in Rhino. And again, even though it was generated in Rhino, it'll still, Shipmo 3D will automatically refine the mesh along where the water line is, which is handy. Let's talk about hydrodynamics pre-processing now. The first step is in the panel lid application. This is usually a very quick process. This is a lid is used to suppress irregular frequencies that can happen during the wave radiation diffraction calculation process. Irregular frequencies are numerical issues that arise with the potential flow solution resolving wave heights inside the ship that really aren't kind of supposed to be there. And very generally, the default settings work really well to generate the lid that's necessary to work with this, so it's pretty straightforward to work with. But if you're working with different kinds of hulls like catamarans, there's a few different options on how to generate the lid. It's generally very quick, and you can view what the lid looks like to make sure it looks good very quickly. The next step is the application called rad_diff. When you're working with a new project, I really strongly recommend you calculate only the wave radiation effects first. This is a great, it's much faster than calculating both radiation and diffraction. What typically you can do is plot the frequency dependent added mass and damping that is resolved from the wave radiation effects. And as long as things are looking relatively smoothly and on these curves and there aren't any big spikes or anything like that, it's usually a sign that you've got a reasonable number of panels and things are looking good. The lid method's working reasonably well. There is a condition number plot that's optional that you can take a look at. The condition number is just a numerical indicator of the stability of the calculations. If things are looking good in the frequency dependent added mass and damping plots, then you don't really need to pay any attention to this. But usually if there are spikes showing up and it looks unusual, this is a good indicator if it might be an artificial effect or not. Sometimes you can see spikes in here where there may be things like wave reflection happening between hulls, like for example of a catamaran at a specific frequency, and those are real effects, and it's not something you necessarily have to try to get rid of, and it doesn't always have a big detrimental effect on the motion analysis, but it's good to know that it is possible to have these physical things that can exist. Now there is a parallel processing option but be careful with it, and it does help a lot, but be careful with it because it can use all your computing resources. So if you want to do other things with your computer, just be aware that that can be an issue. So how can you improve quality of results? Well, typically the best way to do this is by adding more panels as needed. But there are a couple of other tricks you can do. Again, really recommend use the lid method. That's a great way of controlling any issues with noise showing up in the radiation results. But yeah, if they're looking good, then recalculate them and include the diffraction computations. Just be aware that by far this is the longest computational process in SHPMO 3D, but really it depends on the combination of forward speeds you've selected, directions of the waves, and the number of frequencies that you want to compute. There is another application for resolving the effects of slosh tanks. I'm not going to cover these in great detail, but just be aware there's also a sample barge. That's one of the validation cases for SHPMO 3D that has a slosh tank set up in it. Very generally, you need to generate a panel mesh for the slosh tank and then calculate the wave radiation effects of the slosh tank, as it's going to affect the sloshing motion in the tank is going to affect what happens with the vessel. They seem to be fairly straightforward to work with because they define a square tank kind of geometry that you can apply on the vessel. The next application is build ship. And this is where we assemble the final complete ship model. So we include the panel mesh set up previously, as well as the database of radiation and diffraction values. And this is where we start adding appendage models to the hull as well. So it's technically part of ship design because you can change these bilge keels and then evaluate ship motion again. But we're not necessarily doing any pre-processing when we add the bilge keels and skegs and things like that. Typically when you're adding things like these appendages, it's the geometry that you're adding. There may be some, often there's a few settings for the viscous models that are used behind the scenes as well. Propeller data, typically this is added by non-dimensional thrust coefficients. Note that there's an option in build ship also to export a hydrodynamic database model to use with Proteus DS. This is going to provide the radiation and diffraction values, hydrostatic stiffness, and things like that. But at the moment, it does not include propeller information and does not include the viscous models from the appendages. And this is a nice shot showing the generic frigate with a lot of details on the panel mesh that's generated along with all of the appendages. If you wanted to make changes to the appendages based on a ship motion analysis, you can definitely do that here. And then without having to make any changes to the wave radiation and diffraction calculations and go back and then calculate the sea-keeping motions again. That's a very fast process to go through. What is a very slow process to go through is if you change the hull geometry of the ship and then you need to recompute the radiation and diffraction loads. That takes a while, but then that's the process you would go through back again, loading it up in build ship here and then using the build ship model in your sea-keeping motion analysis. So you can see that's why we were looking at both ship design and hydrodynamics pre-processing together. In review, we just reviewed the process overview for ship motion analysis. We covered the applications in SHPMO 3D and specifically the applications needed for setting up and processing ship data, as well as the hydrodynamics pre-processing. And chief among those are, of course, the radiation and diffractions calculations. All right, thanks for your attention. And remember, if you have any questions, you can email us at support@dsaocean.com and we can help you on figuring out what you want to do in the software. Thanks for watching.